So our second traversal algorithm is what we call breadth first search, or BFS. Okay, so in DFS, we explored the graph by going to the deepest possible point that we can before trying to find alternative routes. So in breadth first search, the opposite is true. Okay, so we try to look at uh, all of the shallowest connections first. Okay, what does that mean? So if I have a starting node 1, then I visit all of the nodes that are just one edge away from 1. So that's 2, that's 5, and that's 6. So I mark all these 3 nodes as visited. Okay? And once I've done that, then I ask, okay, what are the nodes that are 2 edges away? Okay? So if I try to take 2 steps from 1, what are the nodes that I can reach that I haven't visited yet? So in that case, if I try to look at all of the nodes 2 away from 1, then that's all of the nodes adjacent to this first layer that haven't been explored yet. In that case, that's 3 and 4. Okay? So I visit those. So I visit 3 and I visit 4. And once I've done that, uh, are there any nodes that are 3 edges away from 1 that I haven't gone to yet? Wala na. Okay? So there aren't any nodes adjacent to 3 and 4 that we haven't gone to yet. So we say that the whole graph has been traversed. Diba? So our exploration of the graph um, can actually be defined in layers, right? So we have our source node 1, and then I look at all of the nodes 1 edge away from 1, and then all of the edges 2 away from 1, and so on. Okay, so when we're traversing edges in the sequence, if we have larger graphs, then we could possibly have 3, 4, and 5, so on. So we try to take a look breadth first. Okay, we explore the whole width of that section before we move on to a deeper layer. Okay, so that's breadth first search. So how do we implement that in code? Kanina, when we took a look at depth first search, we saw that we could implement it using stacks. Okay, either our recursion call stack or a stack data structure. So actually, when we do breadth first search, we use the opposite order. Okay, so instead of last in first out, we have a first in first out order, and in this case we use our queue data structure. Okay, so now we declare a queue. Okay, and then we place our first node, okay, our starting node, into the queue, and we mark that first node as visited. Tapos, while the queue isn't empty, we take a look at all of the nodes adjacent to our starting node, and we push those into the queue. Diba? If we haven't visited those yet, we push those into the queue, and we mark them as visited. And what happens when we do that? Okay, so let's try to go through it step by step. So we have a queue, say, in, out. So we enqueue 1, okay? So 1 is our starting node. Tapos, we mark it as visited. Again, we keep track of the edges that or the nodes rather, that we visited already. So we visited 1, and the order of our exploration, so we start at 1, and while the queue isn't empty, we remove a node, we start with 1, and then what are the nodes adjacent to 1? So again, that's 2, 5, and 6. So if they haven't been visited yet, which at the start, di pa natin siya napupuntahan, so we enqueue all of those nodes. Okay? So we enqueue 2, and we actually mark it as visited once it's been placed in the queue. Okay? So 2 is visited, then we enqueue 5, and 5 is visited, and we enqueue 6, and 6 is visited. Okay? Now, the queue isn't empty, so again, we pop an element of the queue, and once we do that, then we take a look at the nodes adjacent to the one we just popped. So that's 2. What are the nodes adjacent to 2 that we haven't visited yet? So at that point, our graph coloring looks something like this, diba? We visited 1 and we visited all of these in the first layer. So the only node adjacent to 2 that hasn't been visited yet is 3. So we enqueue 3, we place it in the queue, and we mark it as visited. Okay? And at that point, there aren't any more adjacent nodes to 2 that we haven't explored. So we go to the next iteration of the while loop. Okay? The next iteration, we pop 5. Okay? So 5 is the next one we go to. And then we take a look at the ones adjacent to 5. So that's 1, 2, and 4. The only node that we haven't explored yet is 4. So we put that in the queue. So 4 is here. And then we mark it as visited. And wala na. The whole graph is technically visited. So at that point, okay, let's keep on popping elements. Okay? So we remove 6. And then we no longer have any elements to place in the queue. So we just move on to the next while loop. We pop 3. And then we pop 4. Okay? So once the whole while loop is empty, then we say that we've already explored the whole graph. Okay? And this is the order in which we popped our elements, or in which we explored the graph. Okay? So that is our BFS implementation, or BFS function. Okay? Now if you want to convert that into C++ code, we can do this as follows. Okay? So again, I have C++ code here. I have the BFS function. We've declared a queue, and in this case, we print each node once we've pushed it in the queue, okay? And we mark it as visited. So while the queue isn't empty, again, we pop a node, and for every node that's adjacent to our starting node, if we haven't visited it yet, we push it into the queue, and we mark it as visited. In this case, I'm using an adjacency list, okay? So I'm using the map data structure to have a hash table of our adjacent nodes. And we see here that 1 is adjacent to 2, 5, and 6. 2 is adjacent to 1, 3, and 5. So those are the elements in each adjacency list, okay? So if I want to traverse that whole list, then recall our notation for loops like this, diba? Here I map an integer to a vector of ints. So I can actually use our colon representation to select every integer in a vector. Okay? So for every node in that vector, I push it in the list if that has not yet been visited. Okay? And I call the BFS function on my graph using an array to represent the nodes that I haven't visited yet. And let's see what the output of this code is. So I write the file, and I have exactly the traversal that we saw earlier. Okay? 1, 2, 5, 6, 3, 4. So 1, 2, 5, 6, 3, 4. Okay. So that is our breadth first search. Before we end, just a few notes on graph traversal. So in general, our graphs can contain cycles, diba? So in our trees, when we traverse our trees, we don't have a concept of cycles. So when we saw our in-order, post-order traversals, we didn't have to deal with looping paths, diba? But when we have cycles, if we try to implement, say, depth first search, um, if we went um, through that path, right, we went to 1, 2, 3, 4, 5. If we didn't have a mechanism to stop um, our traversal, then we could possibly go on forever, right? So I could see all of these nodes and I could say, okay, let's go back to 1. And we could be stuck in a loop forever. So to avoid that, we maintain a list of visited nodes. For example, the one we saw here. Okay, so it's just Boolean, so we mark it as true if the node is visited or false otherwise. And if we do that, then we can ensure that if we already visited a node, we don't have to go back to it. And our traversal functions will eventually end. Okay? What else? So, as we saw in our depth first search example, if we have a traversal algorithm, we could possibly have different orders of traversal. So, depending on which neighbor we attempt to visit first, then we could result in different orders of node traversal. So, for example, if I selected 5 before 2, then this output order could possibly be different. So, in general, it doesn't really matter what that order is so long as the concept is maintained, right? So, if I have a breadth first search traversal, then I know that these 3 nodes, 2, 5, and 6, will all appear before 3 and 4. I would explore the nodes in this first layer before I explore the second layer and the third layer, and so on. Okay? But in general, if I print this list, then possibly these 3 nodes could appear in any order. So another breadth first search traversal could possibly be 1, then 5, 6, 2, then 4, 3. And that's perfectly fine. Okay? The same thing for our depth first search. So again, I could say select 1 and then 5, and then 2, 3, 4, and then 6. So that's also a valid depth first traversal. Okay? What else? So recall our 3 traversal algorithms. So pre-order and post-order of binary trees are actually both depth first search algorithms. Diba? So if we take a look at our pre-order and post-order traversal, what does that look like again? So we have several nodes in our binary trees, and we could say trace a path. So around the tree from our root. So in this case, if we have a traversal of a binary tree, then we say that the root is the starting node, right? And if I mark the nodes in pre-order, I would mark them here. And then in post-order, I would mark them on the other side. So this way, okay? So if you see here, if I print nodes in this order, right? So let me just label these. So 1, 2, 3, 4, 5, 6, 7. Then if I went into the graph like this, then this actually results in a depth first traversal, right? So we see here that I'm trying to explore this branch first, and then I backtrack, I go back to 2, and then I explore everything that I can still explore from 2. In this case, that's 5 and 6 and 7. Before I go back to 1 and I print 3, right? So this is actually an example of depth first search, okay? Wherein for pre-order, I print each node once it's visited, and for post-order, when do I print the node? Once the branch has been fully explored, right? So when I get from 1 to 2, at this point, pwedeng may mapuntahan pa tayo. So we don't print it just yet. But if I get to 4, okay, I don't have anywhere else to branch to. So once I go back up here, then I know that, okay, napunta na natin lahat ng routes from 4. So I go back 6, 7, and 5. And at that point, all of these nodes have been visited before I print 2. And this whole subtree has already been visited before I print everything else. Okay? So the underlying principles of our tree traversal algorithms of these two traversal algorithms are actually depth first search. Okay? Now, what's an example of breadth first search for our trees? So that's our level order traversal. Okay? So yung level order traversal natin, how does that go? It actually goes in a zigzag manner. So we go from the starting node, and then our first layer, and then our second layer, and our third layer, right? So if I print nodes in that order, so 1, 2, 3, 4, 5, 6, 7, then the nodes that are only one edge away will be printed before the nodes that are 2 edges away, and so on. So this is actually a breadth first search algorithm. Okay? So another thing of note is that BFS can be used to find shortest paths in, unweighted graphs. Yeah. Okay? So if we have an unweighted graph, right, then we say that all of the edges are of equal cost. So if I want to get from 1 to 5, then technically that's twice the length of the path from just 1 to 2. Okay? If I use breadth first search, then I know that if I traverse my nodes, I discover what are the nodes that are 1 away, that are 2 away, and so on. Okay? So I know that 4 and 5 are actually 2 away from my root. And sige, correct natin dito. Unweighted. Yan. So if I take a look at, say, this graph, then I have several paths going to, say, 4. I could go from 1 to 2 to 3 to 4, but I could also go from 1 to 5 to 4. Okay? So, how do I know what my shortest path is? So again, we can just take a look at our breadth first traversal. Okay? So, from this, I know that all of these nodes are only one edge away at the minimum, and these two nodes are 2 edges away at the minimum. So I only need 2 edges to get from 1 to 4. And I know that the path from 1 to 5 to 4 is actually my shortest path. Okay? So if I try to find a path, then that would just involve backtracking. Okay? So which is the node that pushed 4 into the queue? So that's 5. Which is the node that pushed 5 into the queue? That's 1. And from that, I get the shortest path. Okay? So I don't have to go through any other edge. We know that this is one such shortest path to 4. Similarly, from 5, there are several routes from 1. I could go from 1 to 2 to 5, 1 to 2, 3, 4, and 5. But I know from BFS that 5 is actually just 1 away from node 1. Okay? And lastly, again, we say that when we have a traversal algorithm, this gives a spanning tree of the component containing the vertex. Okay? So, again, we already saw what the spanning tree looks like for breadth first search, for depth first search rather. And when we traverse our graph using breadth first search, then our spanning tree would look something like this. So we started at 1, then we visited the first layer nodes first. So those are our connections. And then we visit 3 and 4. So 2 is adjacent to 3, and 5 is adjacent to 4. So this is what the spanning tree looks like for breadth first search on this graph. Okay? So again, in general, if we want to explore our whole graph using traversal algorithms, then we would have to call depth first search or breadth first search on all components of the graph, because these algorithms will only traverse a single component. Okay? So that's all for now on graph representations and traversal.